So today we're going we're going to look at some examples from past exam papers that involve logic gates, and you'll see actually the long questions when they appear, if they appear, are quite easy. In fact, the multiple choice are more difficult than the long questions. But I don't know how many of you have arrived to this section in your studies to look at the logic gates, but these are the logic gates that we are going to be busy with in our problems, and the ones that we need to understand how they work. And we have the AND gate, the OR gate, and the NOT gate, and also another two gates is the NAND, which means not AND. So obviously it relates to the AND gate. So this NAND actually means not AND, and for short we call it NAND. And the NOR gate, which means not OR, as you can gather, not OR, and links to the OR gate. In fact, the NAND gate does the opposite of the AND gate, and the NOR gate does the opposite of the OR gate. Now, I have them separately here, maybe in these bigger diagrams, they might make more sense. Look at the AND gate. What does it mean? It does a logical function that rather let's start differently. If we look at all those gates, we see that all of them have one output. Each and every one of them have only one output. And the type of the output, the signal that they are going to get out, depends on their inputs. Most of them have two inputs, except the NOT, which has one. Sometimes there are gates that have more inputs, but nevertheless, let's concentrate on these two inputs. So most of these gates have actually two inputs. Most of them have two inputs, except for the NOT gate that has only one input. So what the output of a gate is going to be depends on its two inputs, on the signals that we put in. And let's start from the AND gate. The AND gate, what it means is that both the inputs must be, say, a high signal, like a logic 1, for example, for the output to be also 1. So for the AND gate, both inputs, let's call them A and B, if both of them have send the signal 1, which corresponds to the high signal of the on or the true state, the logic 1. If both of the inputs have send the signal 1, the output, which here is X, but usually we represent by Q nevertheless, the output will also be 1. So both the input A and the input B must be 1 for the output to give us a signal of 1. That is why it's called AND. Both of them have to be 1 so that the output is 1. If only one of the inputs gives a signal 1 and the other has a 0, the output will always be 0. For any other combinations, in other words, except for both of them being 1, the output will be 0. So if you look now in all these possibilities of the value of the input and the resulting value of the output, if we put them all together, if we table them all together and record them, make up the truth table of the gate. And therefore, these little tables that we have under each gate here actually represent the truth tables. These are all truth tables. In other words, they tell us what the gate does. So you see for the AND, if both inputs we said are 1, only then the output will be 1. So both A and B must be 1. That is why it's called AND. And you see, if both input and if both inputs send the signal 1, only then the output will be also 1. For any other combinations, which means combinations between 0 and 1, if both are 0, or one only is 0 and the other is 1, or vice versa, the output will always be 0. So this is the truth table for gate AND. Now, the NAND gate does exactly the opposite. That's why it's called not AND. So if the inputs are like the inputs of the AND gate, you see the 0, 0, 0, 1, same inputs as the of the AND gate. The output, it's exactly the opposite of what we expect from the AND gate. So if the AND gate gives us an output of 0, the NAND will give us 1. 0, the other one is 1. 0, 1. And when the AND gives an output of 1, the NAND will give 0. So that is the truth table of the NAND gate. It's exactly the opposite, in other words, of the AND gate. The same applies to these two gates, the OR and the NOR. The NOR does exactly the opposite of what the OR does. So if we understand what the OR does, the NOR will do the opposite. So let us see now, what is this OR? Obviously, it means one or the other. Something like that. So if for the OR gate, if one of the inputs, say sends a signal 1, the output will be 1. It doesn't matter if this is the one that sends the 1, this output, this input or that input, as long as one of the two or both have a signal, send a signal 1, the output will be always 1. So here is its truth table. If both of them send the signal 0, this cannot be 1 because none of them sends an input of 1. So for both inputs 0, the output will also be 0. But for any other combination between 1 and 0 for inputs, if we have if we just one input with sending a signal 1, or both of them send signals 2, send a signal of 1, then the output will be 1. So if this is, for example, 1 and 0, since one of the two sends a signal 1, the output will be 1. So that is why for all these combinations of 0 and 1, 1 and 0, or both ones, the output will be 1, because it's either one or the other must be 0 or both. But if both inputs are 0, the output will be 0. That's the only case where the OR gate will have an output of 0. And now that we have the outputs, all the possible outputs of the OR gate, we see that the NOR gate will be exactly the opposite. For the same inputs, the output will be exactly the opposite of the OR gate. So you see those two are always opposite. This is what's called not OR. Same as the AND and NAND gate. And finally, the easiest gate is actually the NOT gate, which is first here in this picture. And the NOT gate is called NOT because the output is always the opposite of the input. If we send a signal 1, the output will be a 0. If we send a signal of a 0, the output will be 1. And now, because it does exactly always the opposite, the output is always the opposite of the input, this is called an inverter, a logical inverter. And in fact, you see this little circle here in front of the triangle. This kind of represents the inverter. It inverts the logical message sent. And that is why we see this little circle also in the NAND gate that inverts whatever the AND does. And also we see it here at the NOR gate, which inverts the outputs of the NAND gate. That is why the NOR gate has opposite outputs than the OR, and that is why the NAND gate has the opposite outputs of the AND gate. Now, this inverting signals, this inverter is represented by this little circle that we put in front of the gate, in front of the NOR and in front of the NAND, and that is the reason why it's represented. It's also found in the NOT gate, which represents the ultimate inverter. All right, so this is just to remind us roughly to what the AND and the OR mean, and also the NAND and the NOR and the NOT. There are some more gates, but these are the gates that you need to know, and you don't need to know anything more. And perhaps you find strange these logic gates diagrams, but remember this is not how this the logic gate AND, for example, looks like. This is just, it's a circuit diagram, it's circuit symbol. And we also need to remember that electronic circuits, digital and electronic circuits that do this logical functions look very, very different from the other normal circuits, not just the electric circuits, but even the normal analog electronic circuits that we meet. These circuits, the digital electronic circuits, look very different because we only see gates, and they don't look at all like the other ordinary circuits that we have come to be familiar with. And it makes sense because they work completely different. The signals that they work with are completely different because they only work with two types of signals, either on or off, or 1 or 0, these logical bits that we say. And these are the electronic circuits that we meet in computers and laptops and things like that, work with digital electronics. But it doesn't mean that all electronic circuits look like that. I mean, when we use the other electronic components like diodes or transistors or LDRs or LEDs and stuff like that, which are semiconductor-based devices. These are, whenever we use one of these devices in one of our normal circuits that we connect, and we say that we call them electric circuits. From the moment that we have devices based on semiconductor substances like silicon, these are actually the analog electronic circuits. It's only when we have logic gates that we produce digital electronic circuits. So we have these two types of electronic circuits, the analog and the digital. Anyway, this is just a small parenthesis, just to remind us roughly how these logic gates look like. We need to know how to draw them, how to represent them, and we need to know how to figure out the inputs and the outputs. These big diagrams here, I just have to just show the AND gate and the NAND gate, just to see how they behave in the opposite way. So for the same inputs, for example, if the inputs are both 0, the AND gate should give an output of 0, but the NAND gate will give the opposite. What is this? The output should be, dear me, it's the opposite. What is this diagram here? It should be opposite. Yeah, I have it wrong. Sorry, I found it. I Googled it and I see. You see, the NAND gate should give the opposite output. So this should be 1 here, not 0. They have it wrong. Goodness, we need to be careful. Now for 0 and 1, for the AND gate, both inputs must be 1 for the output to be 1. for any other combination of zeros and ones, the output will be 0. But in the NAND gate, for the same inputs, the outputs will be the opposite. If instead of those 3 zeros here, we should have 1, 1, 1, 3 ones, because it does the opposite. And for two inputs which are 1, the AND gate would give an output of 1, but the NAND gate would give 0 because, or it inverts what the AND gate gives. All right. Again, the OR and the NOR to compare. In other words, this gives give us all the combinations, all the possible combinations of inputs and the resulting output. In other words, if we put all these combinations in a table, we end up with a truth table of those gates. Yeah? So remember, for the OR gate, one or the other input must be 1 for the output to be 1. So all these, the last 3 parts where they have at least 1, 1 for input, the output will be 1. Here we have none of the inputs being 1, therefore the output is 0. And of course, the NOR gate will have all of this opposite. What are they doing here? The NOR gate must be opposite. 0, this should be 1 here, dear me. And this should be 0, and this should be 0, and this should be 0. Goodness, I never expected that they will have the diagrams wrong. Okay, guys, I hope you understand this. Eh? So we must take whatever we find on the internet, we must take it with a pinch of salt and make sure that we check it. The moral of the story. Okay, so the OR and the NOR gate, that's the opposite. And lastly, the NOT gate, which is a very useful gate, even if it's so small and so easy. And we see that whatever the input is, the output is the opposite. And okay, I hope now we can use this to start with a problem. Let's start with a long question first. Something that we can find from an exam, like which years that is from 2016. Okay, so what does it say now, this problem? The figure, let's make it a little bit bigger. The figure shows the symbol for a logic gate and its truth table. So here is the logic gate and its truth table. We can see from the shape of it, it's an AND gate. We need to know this by heart. This is an AND gate. All right, so we see, well, since it's an AND gate, remember both inputs must be 1 if the output is to be 1. So we see input A and input B must be both 1 for the output to be 1. For any other combination of inputs, the output will be 0. And we can see that indeed this table confirms that this is the AND gate. All right. Now, state the name of this logic gate, okay? The name is AND. Okay, so we need to recognize, if we cannot remember the truth tables, we need to be able to figure them out by remembering what is the function of the gate. The function of the AND gate is that A and B must be 1 for the output to be 1. So this AND is very important in the name. Now, here is another gate, and we see that there is a logical inverter there. So which gate is this? Well, without this little circle, this would be the OR gate, but now with the inverter, this is the NOR gate, because it means not OR. So complete the truth table of the logic gate shown in the figure. Okay, now, if, you know, it's easier to find the truth table of the OR gate first, and then from there to change all the outputs and to find out the truth table of the NOR gate. So, I mean, I suggest if we are beginners, let us figure out first the truth table of the OR gate first. The OR means that either the A or the B must be 1 or both for the output to be also 1. Okay, so for this to be, for the output to be 1, either this or that or both must be 1. At least one has to be 1, in other words. So if both of them are 0, the output will be 0. Okay, so for both inputs 0, the output will be 0. But for any other combination like 1 0 or 0 1 or 1 1, the output will be 1. So this will be the truth table for the OR gate. Then the NOR gate, the output will be all opposites. So the top will be 1, the others will be 0 0 0. The others will be all zeros. Okay, so here we have our answer for the truth table of the NOR gate. Yeah, correct. I see your answer. Eh? Yeah. The next question now says, the figure shows the system of logic gates used to ensure the security of the strong room of a bank. Okay, suppose where they keep the money. All right, the strong room of a bank. All right. The strong room door will only open when the output F is logic 1. So the door will only open if the output, the final output here is 1. All right. Complete the table to show the logic states of all the inputs, A, B, and C, in other words, all the inputs. We have a combination of gates here. So complete the table to show the logic states of at A, B, C, and D, and also there, and E, when the strong room door can be opened. Okay, so in other words, if this is 1, what can be the logic states of all the others? Of this, the inputs of this gate and also the initial inputs. All right, so this is, we can see it from its shape, it's an AND gate, isn't it? And the AND gate has an output 1 only if both its inputs are both 1. So this has to be 1 and this must also be 1, isn't it? For this to be 1. Okay, now what these ones now are actually the outputs of the first 2 gates here. And this top gate, which is also an AND gate, so it's very easy to find its inputs. So if its output is 1, then both of these inputs must be 1. So already we have that A, B, and D must be 1. So this must be 1, A, B, and D. A, B, D must be all 1. Now let's see the other. Here we have a NOT gate. Yeah? Oh, the NOT gate. The NOT gate. If its output is 1, its input is the opposite. It's 0, isn't it? So C must be 0. And what else? The E is also 1. So these are the correct logic states for the inputs and outputs that they require. We all understand that, I hope. A and B, let me see your answers. The A and the B is 1, yes, correct. The C is 0, yes, correct. Yeah. So you see, these long questions in the exams are actually not difficult at all. They don't, I didn't see very often having long questions on logic gates, but they do have occasionally, and when they do, they're actually easy questions. Here's another one. This one combines light sensors and temperature sensors and so on. Okay, good. The figure is a schematic diagram of an electronic circuit controlling a lamp. Okay, it controls the lamp. Here's the lamp. The output of the temperature sensor is high. So the output of a temperature sensor is high, which means 1, when it detects raised temperatures. Okay, so when it's hot, its output is 1. All right. So 1 for hot. The output of the light sensor is high when it detects raised light levels. So for this one, its output is also 1 if it's high light, a lot of light. Raised lights, okay. Now the lamp is lit when the input to the relay is a logic 1. Okay, so this will light up, in other words, when the input here is 1. So there we have, okay. Complete the truth table by giving the outputs of A and B. The output of A and the output of B. All right, so this is an AND gate, all right. An AND gate. How do you spell AND? Okay, AND gate. So since it's an AND gate, for the output to be 1, its two inputs must be 1. All right, so this is 1 here. Now look, this one is actually the output of this inverter, the NOT. It's a NOT gate, this one, NOT. So if this is 1, this must be 0. Oh, there. Okay, good. So at least we know that the light sensor has to have a logic 0 for the lamp to light. Now let's see about on the top branch where we have the temperature sensor. So here, for this to be 1, you see 1. When does the temperature sensor has an output of 1? When they tell us it's logic 1 when it detects raised temperatures, when it's hot, in other words. So if it's hot, this will have an output of 1. And but the light sensor, its output is 1 if it's a lot of light. But here we need a 0, which means we need low light here, darkness. So we can say dark. So the lamp is lit when the input of the relay is hot. Complete the truth table by giving the outputs of A and B. Okay. So if the output of the sensor, of the light is 0, and the output of the temperature is also 0, the output of A, where are we now? The output of A, here it will be 1, isn't it? If this is 0, this will be 1. And for the temperature sensor, if its output is 0, sorry, if it's, if it's 0, output of light sense, what am I saying? 0, and this is 0, then the output of B is 0. Yeah, because if this output is 1, the output of B, which is the AND gate, is what? Both of them. Sorry, I'm taking. If both those outputs of the temperature sensor and the light sensor are 0, both are 0, what will happen? If this is 0, if this is 0, and this is 0, then the output of this gate will be 0, isn't it? So the output of the NOT gate will be 1, but the output of the AND gate will be 0. So this will be 1 and 0, correct? If the output of the light sensor, if the light sensor gives 0, and the temperature sensor gives 1, then the output of A must be 1, yeah, and the output of B, this is, let's remove the zeros there. If this is 0 and this is 1, come on, 0 and 1, this will be 1, and this will also be 1 then. If this is, if the light is 1, which means it's very high light, if this is 1, then this will be 0, and then this will be also 0. So that will be 0, 0. And if both of them have a given output of 1, so if both temperature sensor and light sensor have outputs of 1, this will be 0. And this will be 1. So the AND gate will give an output of 0 because one of the inputs is 0. So this will be 0. So both of them will be 0 again. All right. So I hope it makes sense. Okay. So in other words, we have to do all the combinations, all the possible combinations. So state the conditions under which the lamp is lit. Well, the lamp will be lit if this output is 1, which means this must be 1, and this must be 1, and this must also be 1, which means this must be 0. So this needs to be hot, the temperature must be hot, and the light must be dark. So hot and dark. Dark. These are the conditions. Oh dear, we need to stop. Let's see if we can have time. Suggest why B is connected to a relay rather than directly to the lamp. Yeah, why there's a relay between B and the lamp? Well, because perhaps this circuit does not supply enough power for the lamp to light up. Perhaps not enough power, or perhaps this lamp is some remote area and we don't have easy access. Maybe so. Perhaps it's a remote lamp, and the normal conditions for when we include a relay in our circuit. Okay, so these are the two answers. So the most complex part here was to do all these combinations here without getting confused of what happens if this is 1 and this is 0. Okay, so I hope it made sense. And we need to stop here, guys. I hope you will enjoy your weekend, guys. Have a very best weekend, and